Part 6. Base switching. To make clear what will be presently shown, the two anti-logarithm expressions on the right are now re-expanded and differentiated like this. A means any anti-logarithm value, including 10 to the L, or e to the L, or the value of any other exponential. This mini-log table will compare the logarithm values of bases 10 and e for a few values of a. Notice the headings. A, which is any number for which we will seek a logarithm value. Lg, the log base 10 values of a. Ln, the log base e values of a. Use your calculator to fill in the common and natural log values for each given value of a. Pause the video to do the work. Here are the numbers. Is there a consistent ratio between the pair of log values for any given a? Begin by comparing the ratios of the ln values to the Lg values on any line where there is a 1. Now check a few other lines. Pause the video. There is, in fact, a consistent ratio of the natural log to the common log for every number a. For bases, e, and 10, that ratio is always 2.3026. This fact is most evident where a equals 10, because here, the common log value of 10 is 1, which is the denominator of the ratio. In fact, there would be a unique ratio between any two sets of log values for any a and any pair of bases. Here's the proof that any pair of bases have log values that have a consistent ratio to one another. Compare a few log values of base 5 to those for base e. Log base 5 of 5 is 1. Find the L value when 5 to the L equals e. Because our calculators provide log values for bases 10 and e, we will arbitrarily select base 10 to solve this. Take the base 10 logs for both sides of the equation. Then isolate L and do the division. The ratio of log base e of e to the log base 5 of e is identical to the ratio of the log base e of 5 to the log base 5 of 5. And this will be true for any other pair of bases. Now, getting back to our original bases 10 and e. The ratio on the left equals the ratio on the right. Note the reciprocal relationship between the log base e of 10 and the log base 10 of e. Above, in blue, you see the numerical relationships. Below, in yellow, you see a symbolic statement of the numerical relationships. Generic notation, with subscripts, is being used. This relationship holds true for all bases. And thus we have the reciprocal formula. Log base b of a equals 1 over log base a of b. Note how the positions of b and a get switched. Now, let's derive another formula. We saw that the ratio of any base e log to any base 10 log is always 2.3026. And we know that 2.3026 is the value of the base e log of 10. Restating that in purely symbolic form. We rearrange the formula so that the two e logs are on one side. The number 10 is now expressed as a symbol b. And the e is changed to a generic d, so that the formula may now apply to any pair of logarithmic expressions with differing bases. This is the change of base formula. It makes it possible for you to find the logarithm value for any base, even though mathematicians only figured out logarithm values for bases 10 and e. Change the following three log expressions to both base 10 and base e. Pause the video. The numerical solutions, rounded variously. The next lesson is about graphing and inverses of logarithms and antilogarithms.